Hello, I'm Paul Hutton, editor of Smart Highways magazine. We're just getting ready to show you another session from JCT Traffic Signals Symposium 2018. But before, let me just remind you of a few things. First of all, if you're at JCT this year or are affiliated to the organisation, you can sign up for a free copy of Smart Highways magazine. Just go to the link at the bottom of the screen. Also, mark your cards for the ITS UK Summit, 26th and 27th of November at the Bristol Harbour Hotel. It will be a fantastic day talking about implementation. And next year, don't forget, Trafex, 2nd to 4th of April. It is the biggest and best Trafex yet. Don't miss it.
Okay. Oh. Good afternoon. This presentation is about public transport priority operations. What we've been doing the last 20, 30 years. A project we did about 2 years ago to enhance public transport priority for trams, and what Maggie's been talking about, a top-down system where we use, or give priority using virtual detectors based on schedule adherence, and sort of using a top-down system. So the priority is requested from a regional computer, and the decisions are made, instead of locally, from a regional computer, as I say, down to a local controller. Just a bit of context, Melbourne's tram network is one of the largest in the world. It has about 250 kilometres of double track. There's some statistics there in regards to the number of trips. For single operations personnel, the main issue is 75% of the network is on a shared environment. So it makes it very difficult to get trams moving when trams are sharing the road with other vehicles. The average speed is around about 16 kilometres an hour. We have one private operator, Yarra Trams. They operate the tram network. There's about 450 trams. Different class of trams. The latest class of tram is E-class. It's about a 32 metre length tram, low floor. Each tram has a transponder, so we're able to selectively detect the trams on that roadway. For buses, there's about 1,800 contracted buses. The two largest private operators are Transdev and Ventura. Ventura has about 900 buses. Transdev operates what we call the Smart Bus Orbital bus routes. So you can see the orbital routes on that map. They're sort of high frequency bus routes, high level of service, they operate longer. They have real-time information at the bus stops. We've been talking to both operators in regards to applying top-down type systems. Getting down into detail now, this is a detector map. VicRoads is the state road authority, and they manage 4,000 signals within Victoria. So that's most of the signals in Victoria. This is a typical detector map at a cross intersection. The rectangles are induction loops. SCATS works on information from those stop line detectors. So it gets information about traffic volume, headway, occupancy, then works out a degree of saturation. So from that degree of saturation, it works out how much or how long the cycle time should be, what the phase split should be, and the coordination. The rectangles that are across, they represent tram detectors. So typically on one approach, you'll have two tram detectors. You'll have advanced tram detector, which is based around about 200 metres prior to the intersection, and then a stop line tram detector. This is the type of configuration we've been doing for about the last 20, 30 years, setting up this operation. So when a tram is detected from the advanced tram loop, it sends a message, it's hardwired back to the controller. There's delay timers, so that if the tram has been delayed, it'll call up an extension or early start phases. If there's a close upstream intersection, we don't need to put an advanced tram detector. We'll sort of use what we call a transfer of demand. So what happens there is when the tram leaves the stop line, it sends a message down to the downstream intersection that the tram is approaching, and then we can run different priority phases. There's about 400 sites that have got some form of tram priority. And just following on from what Transport of London does with route reviews, we conduct route reviews of around about 400 sites every year. We use a similar sort of process. The only difference that we do is we have a movement in place framework, which means that sort of when we do a review, we realise that we can't make improvements for all modes. So a road that has a tram, the hierarchy will be that sort of we try and sort of make the improvements for the trams before we consider other modes. This is, again, getting down to the detail. This is a typical phasing diagram. It's showing 4 phases or 4 stages. A phase and C phase are the vehicle phases. So typically, if trams aren't detected or demanding phases, we'll only run A phase and C phase. If a tram is detected, either by the advanced detector or the stop line detector, then we call up B phase, which is an extension phase. All it does, it extends A phase, so it gives the tram more opportunity to get through the intersection before we run the side road phase. And then we have D phase. That's all one phase, but there's 3 sub-phases. So if a tram is sort of on the east approach, it will sort of call up D1 or call up the right turn phase. So that gives trying to clear out the right turn vehicles before the tram gets to the stop line. If a tram is on the west approach, it'll call up D2. And if a tram gets to the stop line, we don't need to run the right turn early starts, so run D3. So that's just the through early start. If there's 2 trams approaching on the east and west approach, the decision to call either D1 or D2 is based on which direction is the peak direction. So there's rules in regards to when we run D1 and D2 phases. This diagram is just trying to show sort of how we reallocate the times. Maggie talked about sort of time gain, false screens. We use that in SCATs to how we reallocate the time. So the first column is basically showing the phase splits. So you've got A phase, B phase, maybe set up for about 15%, C phase 30%, and D phase 5%. So if the tram priority phases aren't called, the typical situation would be the second column, where you'd have 50% given to each A phase and C phase. And then we can then reallocate the time depending on which priority phase is being called. So the next column is showing the extension phase being called, and the early start call is the second last column, which shows that D phase can run more than 5%. It gains the time with the time gain. It gains time from B phase, but any unused time from C phase. So this is the way we have flexible windows green time allocation by using these time gains and false screens. And I suppose with the way we've been running tram priority, you can see it's fairly disruptive to the side road. The only time we call up the priority is when the tram is running late, and this is why we're sort of trying new systems. We only want to give priority when the tram is running late. I'll talk about that next couple of slides. I mentioned we did an enhanced priority project a couple of years ago. Yarra Trams are very keen to improve the priority for trams. We did an enhancement priority project on 2 routes, Princess Highway East, PHE, from Chapel Street to Glenferrie Hawthorn. It's one of the busiest arterials in Melbourne, carries around about 80,000 vehicles a day. The trams are in their own right of way, so one small part of the network where the trams are in their own right of way. And we also selected Balaclava Road between Peen Highway and Normanby Road It's more of a local road, has about 15,000 vehicles a day. That's where the trams are in a shared environment. So we had two different types of scenarios in regards to trying to look at how we can improve on the priority we give, showing the phasing that I showed in the previous slide. So some of the techniques that we undertook, we terminate the side road phases when a tram is detected at the stop line, measuring congestion on the main road, and then restrict or gate traffic on the side road. We improve tram detection. We're using induction loops. The transponders on the trams send a different frequency, but there's some issues with some reliability of using induction loop with trams. So we tried video detection. We did reprograms to add additional exclusive tram phases. And something we're doing more often is running right turn or counter peak right turn movements every second cycle. Tony mentioned about Perth, about population increase. Melbourne's approaching 5 million people. There's around about 100,000 people moving to Melbourne every year. So we've really got a lot of locations that are very congested. What we're trying to do is squeeze every second out of the operation. So rule of thumb, if we've got a counter peak right turn that has less than 100 vehicles an hour, and there's enough storage space, we'll sort of run that right turn every second cycle, and the time is then allocated to the peak direction. So we'll inform motorists with a static sign that the right turn may run every second cycle. Obviously, over time, that demand may increase, so we have a queue detector. If the right turn goes back to a certain point, we'll cancel that operation out. But as I say, it's squeezing every second out of the operation. When we do our route review program, we put a number of sites in our routes on our website to get public comments, and this type of technique has been really well received. I think people can see that if it's a very low volume, just people are willing to wait that second cycle to give the time back to the peak direction. So it is a technique that we're sort of adopting more often. It's something that I wasn't very keen on, but it's got to a point that sort of it works well, and we got that override with the queue detector in the right turn lane. But the next slide shows maybe one of the issues with doing that. The pick on the left, on my left, is an issue. When you're aggressive with tram priority, you have to also be aware of what the impact of that is. That's Princess Highway. It's got showing the back of the queue in the right turn lane, or it's a short lane effect, it's queuing back into the through lane. So obviously, it becomes a safety issue once we have short lane effects. It also affects the operation for the through vehicles. So it's certainly one issue that we're sort of mindful of. Mention about replacing some of the induction loops. We've replaced them with video detectors. They've been more reliable, but they're still a physical device out on the road network. They still need maintenance, and they're sort of affected by the environment. And also, there were some pretty complex intersections along Princess Highway. Princess Highway, Hawthorn Road, Glenferrie Road. The tram that's completing that S movement takes 2 cycles. So I didn't show the phasing there because it's quite complex, but sort of what we've done is we've added another tram phase in between the diamond phase and the through phase. So we're trying to reduce that delay or the time for the tram to make that S movement from 2 cycles to 1 cycle. So some of the results we got from this enhancement priority project, the parallel vehicle movements in the AM peak the travel time reduced from 9.5 minutes to 5.7 minutes. So it was a reduction of about 40%. In the PM peak, there was a reduction from 7.47 minutes to 5.86 minutes, a 22% reduction. But the corresponding or the parallel tram movements didn't improve because they really didn't pick up the extra time, because their performance regime is they're based on timetable. So if a tram is on time or ahead of schedule, they won't utilise the priority. So this really points to the fact that sort of we should be only giving priority when it's needed, and that's when a tram is running late. On Balaclava Road, we could be more aggressive with the priority. We set up pretty close to absolute priority, so we force off the side road after minimum green or after the ped and clearance had been completed, and basically the trams didn't have to stop at this location at Balaclava Kooyong. But obviously there's an impact, there was an increase on queue lengths on the side road. It's not too bad when the surrounding demand isn't that high, but certainly a technique you wouldn't apply on Princes Highway. Bus priority. What we've been doing with bus priority is, this is just a typical example using the left turn slip lanes. The left turn slip lanes are used as a queue jump lane. Then we have a dedicated bus lane at the intersection. We have a combination of two detectors. They're placed 7.5 metres apart. So what we do, we use the logic of the first detector's activated, stays on until the stop line detector's activated, and that just basically picks up the footprint of a bus. So it's just an easy way of doesn't allow any sort of shorter vehicle to call it the priority. So once we know there's a bus in that dedicated bus lane, we then run an early start, meaning that sort of we allow the bus to start before the adjacent parallel traffic movement, or we might call an exclusive bus phase, which may be sandwiched between side road phases. Okay, the Transnet trial. I've mentioned that Transnet has been developed by a company in Melbourne. It was originally set up in Dublin, but Dublin has done a lot more work in developing their system, and but we're currently doing trials, a proof of concept in Melbourne, and Singapore has also heard about the work that we're doing, so they're undertaking trials as well. We did a trial, a proof of concept on bus route 201, which is from Box Hill Interchange to Deakin University. It's about a 15-minute round trip for the buses. There's only 2 buses that operate on this route, so it was a perfect location to trial Transnet. The GUI on the side, Jason, is just showing the virtual detectors, the buses. Some of the priority techniques we trialled were to run or include a right turn phase in the sequence. Run right turns twice in a cycle. Where there's more critical intersections, we might only increase the split by a couple of %. And some of the minor intersections can be more aggressive with a priority. We had a green window request, which basically forces off the side road and then sort of holds the main road phase until a bus gets through. And that's been quite effective as well. And that's only when the buses are running late. Fairly easy to set up. There's basically 3 windows to set up. The trial that we did, we used our own GPS transponders with SIM cards. The buses have a number of different GPS systems. They have a TomTom GPS system, which gives fleet management data back to the bus companies. PTV, Public Transport Victoria, has their own sort of system to manage the performance of the buses. But the TomTom data had latency of about 50 seconds. The PTV system had a latency of about 20 seconds. These GPS units that we set up had a latency of about 5 seconds. And that's probably the longest latency I'd like to see, because in 5 seconds a bus can be through the intersection and be 60 or 80 metres past the intersection before you deactivate the priority. This is one of the windows in Transnet. There's 4 triggers to activate priority. The first trigger is the number of buses in a virtual detector. The second is the delay time in the virtual detector. The third is if the priority has been requested a number of cycles, it'll be reactivated the following cycle, and then bus lateness or schedule adherence. So you can choose either one of those triggers or a combination of triggers. We've been using delay timer and also schedule adherence or bus lateness. You can block out the priority, so if you want to, you may only want to request it once in every 5 minutes. So there's a fair bit of flexibility in regards to the setup. We've trialled 2 other top-down systems and they haven't been very effective. They've been dependent on bus drivers logging on. They've required third parties to set up the waypoints or the virtual detectors, and they've also had global settings, so they weren't site-specific. With the system, this transit system, we're able to set up priority site by site, so that allows you to, as I talked about before, you can set up different priority techniques depending on the site. This allows, and Maggie showed this before, the window here just, when there's a trigger that has been exceeded, allows us to read an action list which goes through the SCATS ITS port, and we can change any parameter in SCATS. So it can be sort of the cycle time, the phase split, skip phases, add phases, change the coordination. There's a whole lot of things that we can change. We can provide priority at one intersection or as many intersections in that SCATS region. So it gives you a lot of flexibility. There's information about the status of the detectors and also the buses. So it shows whether the bus is stopped, the bus stops in queues, whether the bus has been activated. There's information you can drill down onto the particular bus and find out whether it's on time or ahead of, whether it's late. This is just an example of one of the virtual detectors we set up. This is the first virtual detector we set up in Melbourne. It's a virtual detector on Whitehorse Road between Elgar Road and Station Street. It's around about 500 metres in length. So it gives you a lot of flexibility in regards to the shape or the length of the virtual detectors. And in this case here, the bus is running late. So the virtual detector has been activated, goes through the SCATS ITS port, and then calls up the right turn phase. That's a SCATS access GUI that's showing the right turn. It's got a message line showing that we've changed the phase sequence and the right turn phase has been included to assist the bus on that approach. You can be more aggressive. This is just an example of what we call a green window request. It's a bit like a dwell. So basically what it'll do, it'll force off side road movements without skipping the side road phases, and we'll just hold the priority phase for whatever time that you nominate. In this example, it's 30 seconds. There's also reporting in Transnet. So if there's information about the queue time in the virtual detector, the graph in the middle is showing 2 days. So there's a spike in delay in one of the days. So if you look at, we can go back into SCATS history viewer and then sort of see what was happening at the corresponding time. And what SCATS was trying to do was to run the right turn phase to clear out that whatever was happening on that particular day. So for us, this was a proof of concept in regards to seeing whether this system worked. So far, we've tried different priority techniques. It seems to be working quite well. There's 2 different types of virtual detectors. There's queue detectors and journey time detectors. The journey time detectors just allows us to get information about from point A to point B. So it's an area that we have to do a lot more in regards to sort of getting performance information, but that's something that we're working on. Mentioned a number of things, going through the SCATS action list. There's a number of things that we can do to activate priority. We can extend phases. That can be sort of for any percentage of time, calling phases. If it's a sub-phase, we might have to do a reprogram to have a software flag to enable that. Include different change of phase sequence, increase cycle times, reduce the cycle time, change the linking. It gives you a lot of flexibility in regards to sort of the type of priority techniques that you want to apply. And this just gives an example of the right turn at Whitehorse Interstation. This was just a couple of before shots. I used to take the buses about 3 or 4 cycles to make that right turn. Since we've put in transit with the virtual detector, the buses are now taking 1 or 2 cycles to get through. So just to finish off, we're currently doing a number of projects. We're working with La Trobe University and Australian Road Research Board, looking at using CODA units on the tram. They give us lat-long coordinates, getting information about door closures, but we're trying to optimise when to request the priority. And then we'll do a trial with headway only, so sort of we'll see if we can really get the trams sort of moving quicker through the network. We're talking with Transdev and PTV. The way the bus operators operate each day, buses allocated a different bus route every day. So for us to sort of try and work out the bus ID and lateness, it's going to be very difficult. So PTV are writing an app with their provider to give us real-time information about the lat-longs and the lateness. So that'll make our life a lot easier in regards to just worrying about sort of setting up the priority. We've got a couple of locations where we've got bus lanes, but the headway between the buses is about 10 minutes. So it's not a good use of road space. So we're looking at putting in dynamic bus lanes. So again, using a virtual detector, some electronic signs, when we detect the bus, we'll change operations to clear out traffic in that lane, so it can become a sort of a bus lane when a bus is detected. And we're talking with other sort of bus operators in regards to putting in GPS units and activating this top-down type system. So in summary, we've been implementing public transport priority for many years. When we do operate the way we've been operating, it has a detrimental effect on sort of side road, and sometimes it doesn't provide a benefit for public transport because public transport only needs a priority when it's running late. So with a top-down system, it gives priority when it's needed. You can escalate the priority also, and you can also compensate quicker with a top-down system. And as I said, there's different levels of priority that can be set up site-specific locations. Thank you.
We've also had a crash course in public transport management from Maggie first and now Tony. We are running very tight on time, so one question only, please. So if you've got a question, please move really quickly. Hands in the air. It appears that people want their lunch. I think you've got it politely, Tony. But thank you very much indeed.
I think so.
Oh, sorry. Tony's got one up here. Sorry.
I can hear you anyway.
Yeah, can they?
Oh, sorry.
Do you want to stand up and shout? Yeah.
Yeah, so you talked about stage skipping effectively, phase skipping with the right turns. So what sort of cycle time are you running to phase skip there? Okay. Well, it depends. It's site-specific. The Princess Highway one, we run a 140-second cycle. And it's also, we restrict when we run it. So we do other sort of measures. So it's based on time of day, but it's also based on congestion. So if the peak direction is over a certain congestion level, then we'll enable that operation. So it's only for a small window of the day where we know we have to try and squeeze more out of the operation, but it's site-specific. But the Princess Highway example is a 140-second cycle. So, but people, when we sort of ask the public for their advice or their comments on sort of when we do our read reviews, quite often they'll suggest sort of running, you know, a phase or a movement every second cycle. So it's been really well received. Mm.
Very significant.
Yep, yep.
We got there, Liam.
Tony, thank you very much indeed. Ladies and gentlemen, complete our appreciation for all three speakers this morning.
Thank you. And my thanks too to speakers, all speakers this morning. Thanks ever so much. You've come a heck of a long way. Fascinating stuff.
So, thank you.
Thank you very much, and very pleased
Thank
to
you.
have you all.
Thanks for inviting me.
At the event.
So.
Thank you also to Mark Playdell for an excellent job chairing. Okay. Thank you.
So.
Great.